In this video, we're going to be taking a look at the 2024 AP Physics 1 exam, the FRQ question number 3. So we have a wall here with a string and a beam, and everything is all at rest. So it says the following rectangle represents the beam in figure 1. On the rectangle, draw and label the forces exerted on the beam. Draw each force as a distinct arrow starting on, pointing away from the point at which the force is exerted. So we basically have a few different things to make the net torque zero. We have the force of gravity located at the center of mass. We have the force of tension right along the actual line of where the string is. And then we have the force of the hinge that is slanted in the opposite direction of our Ft, kind of helping with that upward force to counteract the Fg. Next, I drew a little bit extra here on the picture, which we'll kind of discuss later. Actually, we'll go ahead and discuss that now. We have the string that was originally here dotted at space 1, and there was a certain amount of tension, and it has what I called an Ft1y and an Ft1x. The Ft1y is the thing that's applying the counter torque to the force of gravity. And then as that angle is dropped down, we have a much smaller Fty component, a much smaller torque there. So it says we're looking at the string is attached to lower on the wall. At point 2, the beam remains horizontal as shown in figure 2. The angle between the beam and the string is theta equals theta 2. The dashed line represents the string shown in figure 1. The magnitude of the tension in the string shown in figure 1 is Ft1. The magnitude of the tension in the string shown in figure 2 is Ft2. Indicate which of the following correctly compares Ft2 and Ft1. So Ft2 is definitely much bigger, and the reason being is because it had that much smaller vertical component due to its angle. The actual value of Ft has to be much higher. So I wrote the vertical component of Ft2 would be smaller, so the tension would have to increase to counter the torque from Fg. Now, starting with Newton's second law in rotational form, alpha equals the net torque over I. Derive an expression for the magnitude of the tension in the string. Express your answer in terms of m, theta, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference book. So we have alpha equals the net torque over I. We know that there is no alpha because there is no actual movement or rotation of any sort going on. So if 0 equals the net torque over I, multiply both sides by I, which basically drops it. So the net torque equals 0. So that means the torque from the force of gravity is going to be the same as the torque applied by the cable. So here's gravity. It's mg applied to the middle of our beam. That's why it's L over 2. And then our Ft, which is the cable itself, times the sine of theta to get that vertical component times L, because it's acting at the very end of the beam. So I scooted over the Ft sine theta L to the other side, basically rearranged it a little bit. I crossed out the L's cancel out, which leaves mg, and then 2. The 2 is basically in the denominator, and then divide both sides by sine of theta. So then the sine of theta joined the 2 in the denominator, and our Ft equals mg divided by 2 sine theta. Now next, is your derived equation in part C consistent with your justification in part B? Explain your reasoning. So yes, the sine of a smaller angle is a smaller value in the denominator, causing a greater Ft. So if we have a smaller angle in here, then this overall number in the denominator is smaller, and then the entire number itself for Ft is going to be larger. Now this one is pretty tricky here. I had to really think about this one. It says the string is cut and the beam begins to rotate about the hinge with negligible friction. On the following axes, sketch the angular speed of the beam as a function of time for the time interval while the beam falls, but before the beam becomes vertical. So I'm thinking to myself, of course, the angular speed has to increase It's not going to increase in a nice linear fashion. So do I want something that has an increasingly steeper slope or something that has a much more flatter slope towards the end? So I drew a little bit here, which isn't really necessary, but just kind of for you all to see conceptually that my mg, which is causing the torque, is basically acting how it applies torque to the beam, and the amount of torque that it provides is less and less, which means that the angular acceleration that it experiences is going to be less and less. So it's going to have more acceleration in the beginning, and then a little bit less and a little bit less. So then therefore we have a curve that starts up steep and then gets progressively flatter. And that's it for question number 3. So hopefully you did well on that. Thanks for watching and listening.